vamos a hablar de algo que yo. Oh, no, it's in Spanish. It's not in Spanish. Okay, so. Any questions regarding the examples with databases from last class? I think you will never we I think there won't be any examples about that in the mechanical or the cognitive exercises for relations. What we're going to talk about now is what is included in that. So, okay. So then, binary relations are relations, well, between two sets, but we're going to talk about between two sets which are the same set. Then it would be R is a type relation of A with A, or it's a subset of A cross A. For A and an element of A, I can write A R A, or A comma A is a member of R. Those two would be the same notation. Well, would denote the same concept. Okay, we're interested in certain properties of binary relations. One is reflexive. That means that for every element A of A is related to itself. It means that if we have, let's say, 4 elements in A, then the relation has to have at least 4 elements, which would be x comma x for each element of A. It's irreflexive if for every element of A is not related to itself. Okay. If we have that, so I'm going to talk, I know that the next slide talks about this, but if A is, notice that if A is an empty set, if A is the empty set, then any relation, the empty relation over the empty set is both reflexive and irreflexive. Why? It says here is this is the same as saying that R is reflexive. If for every X such that X is in A, X is related to X. Now, what would happen if A were the empty set? Then X in A would be what? What would be the logic variable of X in A if A is the empty set? The logic value, your answer should be true or false. False. And if I have for all X in A such that false, then it would be the by the What's that axiom? It's the empty range axiom. This would be true. So if A is the empty set, then any relation over A would be reflexive, because for all x in A, this would be false. And the same thing, if I had irreflexive, I would have then any relation over the empty set is both reflexive and irreflexive. What it says is for all, be it for all element of A is related to A, or for every element of A is not related to A. Okay, now, symmetric. If A and B are arbitrary elements of A and A is related to B, then B is related to A. That is being symmetric. It means for every element, for elements A and B that are such that A is related to B, then B is related to A. Here you can have if now the empty relation would be symmetric, because we don't have, there are no elements A and B such that A is related to B. Then again, this would be false and the whole thing would be true. Asymmetric. If A and B are arbitrary elements of A and A is related to B, then B is not related to A. And then there's another one, antisymmetric. If A and B are arbitrary elements of A and B, and A is related to B and B is related to A, then A is equal to B. And transitive, if A is related to B and B is related to C, then A is related to C. We're going to see a few examples regarding this. Let's see. Okay. Look at an example. Let's say that R, where I have A is the set that contains A, B, and C, and R is the following relation, one that relates A with A with B, B with A, and C with B. R is not reflexive. Why? For it to be reflexive, it should also contain B and B and C and C. R is not irreflexive. Why? Because if it were, it shouldn't contain the A comma A. R is not symmetric. Why? Because if it were, I have A is related to A and A is related to A. Okay, A is related to B and B is related to B. C is related to B, but B is not related to C. Therefore, it is not symmetric. It is not asymmetric because it contains both A and B and A. And it's not A and B and B and B is not equal to A. It's very easy. If you understand the definitions, then you can, I was reviewing the mechanical exercises for relations, and many of them relate to these. Some of them, they compose relations and they ask properties of relations, but then most of them, if you understand these definitions, then it would be enough. The interesting thing to do for cognitive exercise that you'll probably have is to prove that a relation has a property or does not have that property. So then let's see what you have to do. If you want to prove that a relation is reflexive, what you have to do is for an arbitrary value x of A. If I choose x and I don't say anything about x, and that x is arbitrary, then I can use it to prove that x is reflexive. Let's say I define this relation between integers like this. X is related to R if x is related to y by r. If there's an integer r between 0 and 2, such that x plus r is equal to y. If I want to prove that it's reflexive, I would want to prove that every x is related to itself. Then I take an arbitrary x and I would have to prove that x plus r is equal to x. That means that I can find an r between 2 and between 0 and 2 such that x plus r is equal to x. In fact, there is. R is equal to 0. Then I just proved that that relation is reflexive. If my set is not the empty set and the relation is reflexive, then that relation is not irreflexive. However, if a relation is not reflexive, it does not mean that it is irreflexive, as we saw in the previous example. Because this relation is not reflexive and it isn't irreflexive as well. So it's not reflexive and it isn't irreflexive. So we can see that being reflexive, if the set is not, if it's over a non-empty set, means it is not irreflexive. But if it isn't reflexive, I can't say anything about it being irreflexive or not. Proving that a relation is not reflexive. In fact, is proving that a relation is irreflexive in this case. We have proving that a relation is not reflexive. I have to prove that a relation is not reflexive, I do have to find an element of A such that it's not related to itself. So R is a relation between integers and oh, if there's, assume that this doesn't exist here. I can't erase this, but anyway. So then if there's an R, if there's an integer R such that x plus 3 is equal to y plus r. For 2, if I want 2 to be related to itself, I would need to find I know what I meant there. That is the same condition that I have here, a number between 0 and 2. We need to find a value between 0 and 2, not including 0, such that 2 plus 3 is equal to 2 plus r. But no value will work, since r would have to be 3. Therefore, 2 is not related to itself. Notice that we proved that it's not reflexive. We have not proven that it is irreflexive. In fact, it isn't irreflexive because 1 is related to 1. We have to find an r such that 1 plus 3 is equal to 1 plus r. This r is 2. I don't know what I wrote there. 1 plus 3 is equal to, which is greater than 2, and less than or equal to 2. That's not true. 1 is related. Oh, there should be a 2 here. Okay. Let's write that up on the board or right here so that you can see it. This right exists. x plus 3 is equal to y. So I have this relation. There, I'm saying that x is related to y is the same as saying there exists there exists an r between 1 and 2, not including 2. Then x is related to y if there's an r between 0 and 2, not including 0, such that x plus 2 is equal to x plus r. Now, I want to prove that this relation is not reflexive. It isn't reflexive because if I want to prove that if that 3 is related to 3, I would have to see if there is a value r such that 3 plus 2 is equal no, this isn't right, 2y plus to 3 plus r, but then r is there, it would be related. It's not the, oh, it's plus 3. I would have to find a value such that 3 plus 3 is equal to 3 plus r. I can't find one because that r would be 3 and it wouldn't be in the range that I'm saying there. However, 1 is related to 1. Why? Because I would have to find a value such that 1 it's not going to be related. I think this relation is irreflexive unless because this is always going to have to be 3. Let's write it this way. X times 2 is equal to y plus r. Then x and y are integers. Then 0 and I'm going to change the relation completely. It doesn't matter, but here 0 is related to 1 is related to 1. Now 3 isn't related to let's see. This will work. Now, 5 is 5 related to 5? No, because for 5 related to 5, I would have to find an r such as 5 times 2 is equal to 5 plus r, with r being between 0 and 2. And 5 times 2 is 10. And for And what R would work here? 5, but 5 isn't in the range. However, 1 is related to 1 because I would have to find an R between 1 and between 0 and 2 such that 1 plus 2 is equal to 1 plus R. What R would work there? 1. So then this is an example of a relation which is neither reflexive nor irreflexive. It's not reflexive because 5 is not related to 5, and it's not irreflexive because 1 is related to 1. Okay. Now, to prove that a relation is irreflexive, now you can't really see it here, but this R is crossed out like this. So R is a relation between integers. X is related to Y if there's an X, if there is an R between 0 and 2 such that X plus R is equal to Y. To prove that X is not related to R, we would need to find a value between 0 and 2, not including 0, such that X plus R is equal to X. But no value will work since R should be 0. You notice that, right? I would have to find, let me write it here. I want to see if any X is related to X. An X is related to X if, by the definition, if X plus R is equal to X. By arithmetic, this means that R is equal to 0. And no R is equal to 0 and R can't be equal to 0 because here we said that R had to be greater than 0. So then this relation is not irreflexive, is not reflexive. And in fact, it is also irreflexive because it can't be, because R can never be related to itself. To prove that a relation is not irreflexive, then we have to find a value in A such that A is related to itself. For example, if I define the relation as including 0, X is related to Y if X plus R equals Y and R is between 0 and 2. Now we can always take X equals 2. In fact, take anything. And you find that a number is related to itself, because in this one, this relation happens to be also reflexive. Now, proving that a relation is symmetric. For arbitrary values of A, X and Y, this should be an X. Prove that if X is related to Y, then Y is related to X. For instance, I want to notice something. You should remember that you define sets with a predicate. You can also define relations with a predicate. If that predicate is symmetric, it's an and, or it's an intersection, or it's some operator which is symmetric, then the relation is symmetric. Then I define a relation between sets of integers, that means parts of integers. I say that a set is similar to another set R if there is an element R of the integers such that if it is an element of S, then it's an element of R. Then what I have here is, notice, how do you translate, remember, if I have the existential quantifier, how do you read this colon here? Like an and or like an arrow? If I have an existential quantifier, how do you read those 2 points there? as an and. So there exists an element r in the integer such that r is an element of s and r is an element of r, because this isn't a for all. Then I apply trading twice. This should, and I say that r is similar to s. Or if you want, I only apply trading once, and then if I just read it as an and, the and is symmetrical, then we do have that the relation is symmetrical as well. To prove for now, look at this case here. I'm defining a new relation. X is related to y if x is equal to 2r plus y. If there's an r such that x is equal to 2r plus y. I haven't constrained the value of r. R is just any integer. I want to see if this relation is symmetrical. Notice I have to prove that if x is related to y, then y is related to x. How do I do it? I start x is related to y. Then I know there exists an r such that x is equal to 2r plus y. Now, by existential instantiation, I say x is equal to 2 times r hat plus y. By arithmetic, I put the y, I subtract y, I subtract 2r from y here, and then I switch sides and I say that y is equal to 2 times minus r plus y. Now, if r hat right here is an integer, minus r hat is also an integer, then I could generalize with the existential quantifier, and I say there exists an r such that y is equal to 2r plus x. Therefore, because of the definition of the relation, y is related to x. So then, it is quite, notice what I did here. I defined, I took the definition of the relation. I applied existential instantiation, so then this value is a particular r. But then if I multiply that r minus 1, that minus r hat is also an integer. So by arithmetic, I multiply this by minus 1, I subtract it and take it here. And then I switch the equation around, and I get y is equal to 2 times minus r plus z. And there, minus r, since r is an element of the integers, minus r is also a member of the integers. So I can use existential generalization, and I get that there is an r such that y is equal to 2r plus x. Therefore, and this is the same as saying x is related to y. I mean, y is related to x. This should be y is related to x. I'll fix this presentation, and I'll upload it so you have it correct. Now, yeah. It's right. You can keep the, if I keep the no, I use it for minus r, but r is also an integer. But I'm saying if r hat is an integer, minus r hat is an integer. Yeah. Oh, I don't have to keep the expression. I don't keep the minus. I just keep the minus r is an integer. Is the integer I found. I found an integer which is minus r, and then I say there exists an integer. No, because I need to get to this. There is an r such that this. This is what I have to get. If I kept it, then I wouldn't have the definition here. Proving that a relation is not symmetric. If I say that there is an r greater than or equal to 0 such that x is equal to 2r plus y, then I would have, how do you prove that a relation is not symmetric? You have to show a counterexample. In this case, r is related to 3 is related to 1 because 3 is equal to 2 times 1 plus 1, but there is no integer greater than or equal to 0 such that 1 is equal to 2 times r plus 3. this integer is -1, and it is not greater than or equal to 0. Then, to prove that a relation is not symmetric, you have to use find a counterexample. Now, to prove that a relation is antisymmetric, I want to prove that if x, notice that I have to prove that if x is related to y and y is related to x, then x is equal to y. That's the way you would prove that a relation is antisymmetric. So then let's look at it here, how I would do it. Okay. So my two hypotheses are x is related to y and y is related to x. By the definition, there is an r greater than or equal to 0 such that y is equal to 2 times r plus y. And there is an r greater than or equal to 0 such that y is equal to 2r plus x. I'm going to instantiate them, but it is important to notice that when I instantiate them, I can't use the same r hat. I'm using, there is an r hat greater than or equal to 0 such that x is equal to 2 times r hat plus y, and there is a t hat greater than or equal to 0 such that y is equal to 2 t hat plus y. Now, by Leibniz and composition, I'm going to compose r is greater than or equal to 0, t is greater than or equal to 0, and y is equal to 2 times t hat plus x, but x is equal to 2r plus y. So then I get this here. Notice that I have a y here and a y here. I can cancel them out and turn the equation around, and I have that. I subtract y from both sides, and I get that 2t plus 2r is equal to 0. By arithmetic, I have that t plus r is equal to 0. If t plus r is equal to 0, and t is greater than or equal to 0, and r is greater than or equal to 0, the only way that I can get 0 by adding two numbers that are greater than or equal to 0 is if they both are 0. If t hat is equal to 0 and p and r hat is equal to 0. Now I'm going to replace these values, t and r, in equation 5. So I would get 0 is greater than or equal to 0, and x is equal to 2 times 0 plus y. And x is equal to, I can just simplify, or I can say that this is true. And then by identity, I'm left with only this part of the equation. And I get that x is equal to 2 times 0 plus y, and x is equal to y. It is very important that you understand this proof. Notice what I did. I took x is related to y, y is related to x. This means that there is, if I take this, there is an r greater than or equal to 0 such that x is equal to 2r plus y. And because of this, there is an r greater than or equal to 0 such that y is equal to 2r plus x. I instantiate with r hat. R is greater than or equal to 0, and x is equal to 2r plus y. T is greater than or equal to 0, and y is equal to 2t plus x. I'm going to take these two, I compose these two, and I'm going to replace 2 times r hat plus y for x in this equation, and I get y is equal to 2 times t hat plus x, which is 2r plus y. Now, I subtract y on both sides, and I get that 0 is equal to 2t plus r, which is equal to saying that 2t plus 2r, which is equal to say 2t plus 2r is equal to 0. I cancel out the 2, and I get that r plus t is equal to 0. However, since t is greater than or equal to 0, and r is greater than or equal to 0, if the sum of these two is 0, the only way that can happen is if r is equal to 0 and t is equal to 0 as well, of course. And I have these. Then I'm going to replace this value here in equation 5, which is this one. And I get 0 is greater than or equal to 0, and x is equal to 2.0 plus y. This one cancels out by simplification or simply by identity. Y is equal to 2 times 0 plus y. That means 2 times 0 is 0. It means that y is equal to x. Any questions regarding this group? Remember that, yes. Step what? This one? I'm using many things. First, I compose them. I compose this one and this one. And I apply Leibniz. I say x is equal to 2r plus y. So I replace 2r plus y in this x. So y is equal to 2t hat plus x. But what is x? It's 2r plus y. If I know that x is equal to something and y is equal to something that includes x, I can replace this something for x in this equation. The thing is, this step is like 4 different steps, like 3 different steps. But then I'm using it. And then any other question? And I also use Leibniz here, using r is equal to 0 in this one. Let's look at this example again. Pardon me? T hat is the one that if I know that something exists, I say let this be a value that makes that true. That's part of what you have to know for the past exam. It's a substantial substantiation, and it has a hat because it isn't any R. It's a particular R that makes this true. Do you have any questions regarding the problems with partial orders and total orders? Do you understand what that means? Have you read the book, the class notes? I want to see another example so you'll get an idea of things that we want to do. Let me. Oh, I didn't show you something really interesting about this before going on with old midterms. Let's look at this relation because I haven't really given you examples of a relation of transitive relations. Do you believe that this relation is transitive? If a set S is similar to a set R, and that set R is similar to a set W, do you think that S is similar to W? Yes or no? Well, we're not going to use Socrates test, but take a guess. Is this relation transitive or not? It is. If S is related to R and R is related to W, then you believe that S has to be related to W? Yeah, for example, give me an example of three sets such that R, S was related to R is related, S is similar to R is similar to W, but however, S is not similar to W. If you want to show that a relation is not symmetric, you have to do it with a counterexample. Why don't you try a counterexample for this? Numbers. For such that S is similar to R is similar to W, but S is not similar to the W. 1, 2, 2, 3. So S is similar to R is similar to T, however, S is not similar to T. Then it is not a symmetric relation. Proving that a relation is what happens with these types of relations? This is a relation, again, of known sets between sets of integers. S is a subset of T. Now, this relation is this relation symmetric? If for it to be symmetric for all sets, if S is a subset of T, then T must be a subset of S. Is this relation symmetric? For example, the set that contains 1 is a subset of this set that contains 1 and 2, but 1 and 2 is not a subset of 1. Is this relation antisymmetric? Antisymmetric means if S is a subset of T and T is a subset of S, then S is equal to T. Of course, this is a definition for equality, and you know that that is true. But then it is an anti-symmetric relation. However, this relation, proper subset, is a asymmetric relation. If S is a subset, a proper subset of T, then I can conclude that T is not a proper subset of S. Why? Now, T is a proper subset of S. Okay? It means that there is an x in T that is not a member of X, or T is equal to X. So, however, we already said we want to prove that if S is a proper subset of T, then T cannot be a proper subset of S. And I want to see if I can prove this using something else. You know what I'm saying? T, X is there is an X in T such that X is not a member of S. Now this is false. Why is this false? There is an X in T such that X is not a member of S. But what did I assume beforehand? I want to prove that this is true. Then I would have to prove that there is an X in T that isn't a member of S, or that T is equal to S. However, I know that T is different from, is not equal, right? And this would be false. Then is there an X in T such that X is not a member of S? What do you think? What do we want to prove? We want to prove that this is what I want to prove. proper subset of T, then T is not a proper subset of S. This is what we're trying to do. How can we prove this? To prove that something is not a proper subset, I have to prove that there exists another that is not a member of S. Or if you want, let's just do this. I want to prove that this, that, how do you prove it? When we're trying to prove things like that, what are the techniques that we've taught you? How do you do that? By definition, what we're trying to here, it's kind of complicated. Sometimes it's easier by contradiction. But in here, I would have to say that there exists an X and T such that X is not an element of S, or T is equal to S, but we know that this is false because of the definition. Then I would have to find an X and T that is not a member of S. Look at this drawing here. S is a proper subset if what? If S is a subset, but it's not equal, which means what? Means that I know it is a subset. I know that every element of S is in T. But if they're not equal, it means that there is some element in T that is not in S. Right? Why? Why did I use that? Right? And here we have, using this, Two sets are equal. If x is a and x is an element of S, it can only be x is an element of T, which is the same thing as saying x is an element of S implies that x is an element of T, and x is an element of T implies that x is an element of T. However, I know that this is true, right? Look at this. And now, this is the definition of being a subset. And this too, so. And it's not a subset of this. I could have gotten environment there much quicker if I didn't really have to do this definition. No, we just do it here. There's another property that we have of this. We could this is a subset of T, and T is not a subset of S because it would be that way it would be equal. then I want to okay. So what is T is a subset of not T, subset of S, or T equals S. Now, another definition of proper subset is that it is a subset a subs, if a set is a subset, then it can be a proper subset or it can be. So here by De Morgan, right? I don't need the parentheses anymore because this is an and this is an and. Now, I'm going to take this here, which says that this one and this one, but with this whole expression here is negative absorption. You have S is an element of T, and T is S is a proper subset of T, and T is different from S, and T is not a subset of S. And by simplification, then I get that T is not a proper subset of S. Kind of a strange way to do it, but anyway, we would have to prove this to prove that if S is a proper subset of T, then T is not a proper subset of S. No, if oh, we could also have done it. No. If I want to prove that it's asymmetric, I can't do it without it. I'm not proving that it's not symmetric. I'm proving that it is asymmetric, which means for arbitrary sets S and T, if S is a proper subset of T, then T is not a proper subset of S. You have to do it this way. As I said, I kind of there might be a, like the problem that you had with in your lab, that there may be a shorter way to prove this, but then this one was a way that occurred to me right now. There may be a shorter way to prove this. Anyway, this is the way you would prove that a relation is asymmetric. Now there's an easier one. I can prove for integers, if x is less than y, then y is not less than x. Of course, that is. x is less than y, then what do I know? Right? That I know that x plus r is equal to y. I would have, let's say I know that this is true. Right? And what else do I know? What happens with this r? It's greater than 0. Do you think it is possible? No. Arithmetic? Y is equal, y plus minus r is equal to x, right? However, this is the only number such that y plus this number is equal to x. What happens with minus r? Minus r is less than 0. Since the only number that I found that I can add to y to give me x is less than 0, then I know that there isn't a number greater than 0 that I can add to y to get x. Therefore, it's anti-Semitic. In integers, it's easier. I know in integers that that is the only r that works. Okay, so then let's look at these exercises. Oh no. Next class, I'll upload all the exams so that you can look at them. Next class, we're going to look at, I'm going to give you the definitions of partial order or total orders, and we'll see some exercises. Very fast, maybe some exercises, see some Socrates, and then I'm going to give you the definitions for functions, special functions, although we already discussed them. Injective, surjective, injective or one-to-one, surjective or onto, and bijection, and what it means to have a bijection. Yeah, that is both injective and surjective. If I have a bijection, if I have a function that is both bijective and surjective, what does that mean? What happens with the number of elements? What can I deduce? That their sizes are the same. I can prove that the integers are the same as have the same size as the natural numbers. Even if you would think that the integers have twice the size of the natural numbers, no, the same size. And I can prove that n cross n is the same size as n. However, any new cube, same size as n, but not r. Q, the rational numbers, but not r. Okay, so the next, wait a second. I thought that I needed to use your lab class for this exam. You won't be using it. Our exam is going to be. Let me tell you when our exam is going to be. Calendar.